1102. This is chapter 28, and this is on what we call quantum mechanics. And this is all based on, this will be a lead to what we have, the periodic table, and why it is what we have, all right? So, now if we go to the periodic table was developed in 1869 by Mendeleev. I'm not sure, I don't think I have his name spelled right, but that's okay. Mendeleev, 1869, by looking at the properties of elements and putting them into groups of common properties. And so that was developed in 1869. The question is explaining why this was. All right, at the same time, we talked about earlier that light, so photons, which is light, photons, and electrons, and we'll also see protons, both have a particle nature, particle and wave. Right? So, the way they did this, now we did fraction, we looked at the fraction of light, interference of light, and you get this wave nature to it, so you get interference patterns and diffraction patterns. But what they also discovered is electrons, even though an electron's a particle, it has a wave nature to it. And so what they did is an experiment, and the experiment here was by taking electrons one at a time, shooting them one at a time through two slits. Shooting them one at a time, and they had the option of two slits. As you notice, even though you shot them one at a time, it first looks like a pattern of particles, but eventually started developing a wave, an intensity pattern of light and dark, much like interference. So much like interference, which is due to waves, right? Go through two slits, you would end up with this interference pattern on a screen of light, dark, and so on. So light would come through, and they realized electrons did the same thing. So electron is also a wave, right? It's not just this little ball, billiard ball, but it actually has a wave. So there's actually some spread to it. And so what does this mean? It means that because there's this wave, there's no, you cannot define the position of this particle exactly, perfectly at the small scale. Now obviously with large scale, like I can measure the position, say, of this thing, put it right there. I can measure the position of that to the nearest nanometer if I want to. I mean, to an extremely small level, I can measure that position. I can also measure the speed. If it's moving, I can measure the speed and its position extremely accurately at the same time. We do that in physics a lot. You measure a car moving down, you can measure the location of it and how fast it's moving, which relates to its momentum, all at the same time to extreme precision. All right, on the other hand though, remember we have x, so we define position x and a momentum p, which is given by mass times velocity. And for a car, all right, this can be extremely accurate. All right, you're not going to have any uncertainty, even though there's sort of a wave nature to a car. It is so incredibly small that it's impossible to measure. But for an electron, which is really small, I mean, it's very tiny to begin with, so these effects become much larger. What that means is, because electron is really tiny, All right, to be able to measure it, you have to be able to do something to it. I mean, when I measure the position, if this thing is moving, a car is moving, I have to hit it with some kind of light, whether it's a radar, something to detect its position at a speed. I got to hit it with something. Now, light doesn't take, is so light, it's not going to do it. It's not going to knock the car over. It's going to have no effect at all. But on an electron, if I hit a photon of light to an electron, it's going to move it slightly or affect it slightly. And in that case, I'm not going to be exactly sure where it is. So there's going to be some error in its position, delta x. Likewise, because this light has energy to it, again given by E equals hf, as energy, it's going to affect how fast it's going. So it's like hitting, you've got something moving, and the way you detect it, like, you're running, and the way you detect it is you throw bowling ball at it. Well, if you're a bowling ball and something throws at you, it's going to definitely affect your speed. It's a similar type of thing. So its speed will be affected, delta P, based on this interaction. So what this means is, if we try to be more precise trying to measure its position, say in space, we're going to have less accuracy in how fast it's actually going. And this expression, it turns out the product of these two is always greater than or equal to h over 2 pi, where again h is Planck's constant, given by 6.6 times 10 to the 34th seconds, joule seconds. All right, so that's what h is. And this does become a major factor with electrons and protons. Remember, electrons are very small. They're on the order of 10 to the minus 15 centimeters, and they're not moving very fast. I mean, they have so much, since the mass of an electron is 9.1 times 10 to the minus 31st kilograms, even if it's going very fast, it's going to have a very small position. It's going to have very small momentum. So this becomes rather significant, and this was known as the Heisenberg uncertainty principle. Meaning, you cannot, theoretically, if you can measure the position and speed of every single atom, you could predict exactly what's going to happen with the universe. But since you can't get extremely precise, that's why we get chaos developed, and you can't be exactly certain where everything is. So this is a Heisenberg uncertainty principle. So it's given in terms of that, and if we have energy, then it's given by delta E times delta T is h over 2 pi. So this would be the uncertainty in the energy, say, of a state, where it's at and how long it actually stays there. So that's Heisenberg uncertainty principle there. Okay, so that's it as far as that's concerned. So I can do so let me look at one example here with this, as given in the book. And what we have here is we have, electron moving at a speed of 10 to the 6th meters per second, and the uncertainty in, uncertainty of the speed is 0.1%, which is 10 to the minus third. So this would be delta V, delta V would be 10 to the third meters per second. So it's how accurate you have that speed with that kind of accuracy. Delta P then would be M delta V, which would be 9.1 times 10 to the minus 31st times 10 to the third would be approximately 9.1 times 10 to the minus 28 meters per second. Kilogram meters per second. Let's just drop the units. All right, using that, then X would be actually H divided by 2 pi. This is actually roughly 1 times 10 to the minus 34th. So if I then solve for the uncertainty in X, all right, X is going to be delta X will be equal to H over 2 pi divided by delta P, which is approximately 10 to the minus 34th over 10 to the, let's see, this is approximately 10 to the minus 27th, 9, say minus 27th, that's 10 to the minus 7th meters, all right? Well, the size of an atom is 10 to the minus 10th meters. So if an electron is orbiting, you have an uncertainty here of 1,000 times bigger than the atom, which is a big problem. So that's not very accurate at all. So if you're going to have to do it, you're going to have to do this with much better precision as far as that's concerned. You wouldn't know where the electron is within that kind of factor. So that's the example of the uncertainty principle for very small cases. Now we could also do with something like a baseball, but you'd end up with a number so incredibly small, like delta X for a baseball. You can work this out yourself. Take the average baseball, throw it at 30 meters per second. Delta X is on the order of 10 to the minus 34th meters then. All right, well that's so incredibly small. I mean, that's totally immeasurable. So on the so in real life, you don't see it on a large scale, but on the small scale, the atomic scale, this is a very big deal. So, it deals with lifetimes of states. This gets into other things related to chemistry, high energy physics, effects of that. Okay. Now, I'm not going to get into that, but what it actually means is if we have an atom, all right, rather than the electron being orbiting in a specific spot, there's what we call probability of where it is, with most likely being at the state it's supposed to be in, but it can be anywhere in this spherical cloud or cloud based on these energies. So when you see energy states like S state, P state, D, F, and so on, these little orbitals, that's actually a probability density. It's not the actual path it takes. So that's related to that. And so then I'm going to get into how we do the periodic table here. The last part, chapter 28. We got that. Okay, so we have our energy states, we did before from chapter 27. E sub n is minus 13.6 eV over n squared, where n is 1, 2, 3, and so on. All right, so that's the energy states, and 1, 2, and so on. All right, these are what we call principal numbers. All right, for each n, now I'm getting into the periodic table. All right, there's also this orbitals, right? Then for each state, there are orbitals. All right, you have the S state, you have the P states, all right, you have D state. If you look up the orbitals, and I can't sketch it very well, but the different states, all right, you have these kind of orbitals, right? These are the orbital, these are dependent on different characteristics of each state. And what's related here then is we have orbitals, then we have magnetic orbitals, and then we have spin of electrons. Electron has what we call a spin, like angular, and either has plus a half or minus a half. So an electron can either be spinning up or straight down. It can't be anywhere in between. So an electron spins up, spins down. And what it turns out, if we put all this together, and I know I'm cutting a lot, is there are what we call principal quantum numbers. All right, quantum numbers for electrons. And we'd start with n equals 1, 2, 3, 4, and so on. Then we have L. Okay. And L can go from 0, 1, 2, 3, all the way up to n minus 1. Right? And then M sub L goes from minus L to minus L plus 1 up to 0, all the way up to L minus 1 up to L, right? And then finally we have M sub S, which is a spin, and this can be either plus a half or minus a half. So as an example, let's take n equals, well, if n equals 1, then L can be 0, that's it. M sub L is 0, but M sub S can be 1/2 or minus a half. So that is what we call the ground state. Meaning you can have electron, so that's it there. So everything is in the S state, ground state. And what it turns out is Wolfgang Pauli developed what we call the exclusion principle. And this is that no two electrons in an atom can be in same state. So what this means is for the ground state, we can have a total of two, we can either have one electron, so for n equals 1, we can have one electron, and that would be hydrogen. So one electron, one proton. Then, because for n equals 1, the ground state, and this, we can have electron be half or minus half, we can actually add 2, and this is helium, and that's 2 electrons. We can actually, and that shell is filled. So that explains why the first row, and if you look at the periodic table, our periodic table, the first row is hydrogen on one side, helium on the other side. And that fills it. Right? So, I'll erase this a minute. So that's it. Now for the next one, n equals 2, L can be 0 or 1. Again, this is that. M sub L can be L equals 0, it would be 0. And for L equals 1, it could be minus 1, 0, and 1. All right? And then for each one of these, you can have 2 electrons. So times 2. So this would be 1, 2, 3, 4. 4, 8 electrons possible. So we'll fill up the next one with 1. That would be sodium. Okay? Or lithium, I should say. So the next one then would be lithium with 1 electron. So that's 3. And then we add another electron. So there's 2 there, 2 there. That would be beryllium. And we add 1 more, and that's 3, and this becomes boron. Yeah, I can remember. B. We add another one, that's 6, and that's carbon. So we got 2, 1, 2, 3, 4. And we add another one, and that would become then nitrogen. Then we add another one, 8. Now I'm not saying if we add each one with just that, it's lithium. We add 2, that becomes beryllium. We add 3, that becomes boron. We add 4, that becomes carbon. We add 5, that becomes nitrogen. 6, that becomes oxygen. Add 7, that becomes fluorine. And then we add 8, and that becomes neon. And that's a filled shell. So we have 2 here, 8 here. And then that's neon, which is the 10th element. And it's filled. This also explains why these so-called helium, which is 2, it's a filled shell. Neon is a filled shell. These are called noble gases because for each of those elements, they're a filled shell. All right? Now, related to this, or added, we have these quantum numbers. So for S, a little bit on chemistry, we a lot of times define for L is 0 is an S state, L is 1 is a P state, L is 2 is a D state, L is 3 is a F state, and L is 4 is a G state, and L is 5 is an H state. So that's the letters corresponding to the L. So that's how you end up with, say for Let me run out of room here. So for hydrogen, its ground state is defined as 1s1, where we have N is 1, L is 0, and it's got one electron. That's hydrogen, I should say. Helium is 1s2, right? Next one, lithium, be 1s2, and that would then be 2s1, right? That's its ground state. Beryllium would be 1s2, 2s2. Boron, 1s2, 2s2, 2p1, I believe. Yep, and so on. So that's how it fills up all the way up to neon, which would be 1s2, 2s2, 2p6. Then you go beyond that, and that's how the periodic table develops. And that's how it works as far as that, using these four principal quantum numbers. N, L, M sub L, M sub S. M sub S. And that is the periodic table. And while we're at it, explain one last thing here. So that's the periodic table. Part of the questions will be related to if we have, what is the spectrum for, or the configuration for different elements. And it's not quite as simple as just filling that up. There is a formula for doing that, and you can use a periodic table for that. Okay, so that's the periodic table and quantum numbers, and this is all based on physics. And it works very well. All right, last thing here is dealing with, this is kind of a little out, but if you're in energy, all right, and X-rays, and my wife, when I was doing dental hygiene studies, X-rays, Brem, make sure you're right, Bremsstrahlung, radiation. And this is, and I'm not going to get into details, but this is based on the fact, if we take an electron, right, and shoot it through a voltage, so plus, minus, so it goes flying through and hits a barrier, it's going to stop suddenly. Right? When it stops suddenly, this is going to be a high deceleration. An accelerating particle emits radiation. And the way this works then is based on how fast it is going originally. When it stops, it will produce radiation. And if it's going, say, on the order of, if this is 10,000 volts, all right, in an X-ray machine, so it's 10,000 volts separating these two, right, that's voltage. This electron will have an energy, kinetic energy, given by voltage times E, and in this case it will be 10,000 electron volts. So one electron in a voltage, whatever the voltage is that many big volts. This is a very high kinetic energy. So when it slams into it, it's going to emit a very high energy, and this will actually be in the form of X-rays, usually. So that's how the principle of making X-rays are, is you take accelerate electrons to very high speed, slam them into something, and it produces X-rays, and that's what we call Bremsstrahlung radiation. So that's the case if they're also orbiting, particles are orbiting, their accelerating is going in a circle, given by acceleration is v squared over r, they will constantly emit radiation that way. This is what we call synchrotron radiation. Okay? And that's, as it orbits, it's emitting radiation as it goes in the circle. So it's actually losing energy just by, a charged particle going in a circle will lose energy just by going in the circle. And that is basically the basis of chapter 28. I'm not going to get into any other principles there. So that's it there. We're going to be skipping 29. That gets a little complicated as far as that gets chemistry, potential energy, molecules and stuff, but I'll save that for your chemistry courses.